Mr. McBrien. This is SCH4U, competing for electrons. So the Ontario curriculum says that we need to be able to predict the spontaneity of redox reactions. This is one aspect of it we're going to talk about today. Okay, I wonder how many of you remember day one when we talked about putting solid copper into a solution of silver nitrate. When we did this, the copper over time reacted with the silver nitrate, producing a gray solid on the surface of the copper, and the solution turned blue. And this was associated with the oxidation of the copper and the reduction of the silver. And the reaction is given here. Solid copper reacting with silver ions to produce solid silver and copper nitrate in solution. Okay, it may have occurred to some of you at the time, why is that the reaction that occurs? Why is the copper oxidized and is the silver reduced? Why wouldn't it work the other way around? Okay, the answer to this question is not what you might be tempted to say. You might be tempted to say, well, the system reaches an equilibrium. In fact, no, it doesn't. That reaction will proceed to completion. The answer instead is more that around the idea that silver ions want electrons more than copper solid does. So what happens is the electrons are pulled away from the copper. The copper gets oxidized and the silver is reduced. And like I mentioned, this isn't an equilibrium situation. Early on, there's plenty of copper 2+ in solution as well as the reaction proceeds. However, we don't see silver getting reconverted into Ag+ and copper getting reduced to the metal form again. So, to say that again, it's not an equilibrium situation. So, if it's not an equilibrium, and we can't have an equilibrium constant for this reaction, what's governing this? How do we predict which elements are going to want the electrons more? Well, that's really the subject of our discussion today. If we have a solution containing several components, we want to know if a redox reaction is going to occur, and if so, which components are going to be oxidized and which ones are going to be reduced. And the question is, how do we predict that? Well, we have to look at each metal from the point of view of its willingness to be oxidized. And remember, when we say willingness to be oxidized, we mean its willingness to give up an electron. And of course, everything is a push-pull. So we can also say different metals have different desires to acquire electrons, to be reduced. And this is closely related to the electronegativity of an element, but it's not exactly the same thing. What we can say, and what we do say, is that metals that are more active will easily lose their electrons. They will easily be oxidized. And we categorize metals as being less active if they want to keep their electrons. And it's this willingness, this activeness, that determines how metals in a mixture will compete for electrons. So if we've got a soup of components and they're going to compete for electrons, we can determine what's going to happen based on this, the reactivity series of metals. So this table applies whether we have a soup of ions or whether we have some ions and some solid material in contact with solution. If we want to determine what happens next, we turn to our reactivity series. So, if we want to think back to our case of having solid copper in solution in contact with a silver solution, we can see that silver is one of the least reactive metals. It really wants electrons, and it'll pull electrons from practically any metal. Now, in contrast, copper is slightly more reactive. And what this means is that silver is going to, when in its ionic form, it's going to happily take electrons away from the copper in order to form its reduced version. So let's look at an example. Look at another example. What if we put solid lead into an iron sulfate solution? And this is a perfectly valid question for you to be asked. What will happen? And I might ask you to give me the redox reaction that occurs, if any. What you have to do is, before you start balancing reactions, you have to decide if there's going to be a reaction. And you do that using this table. So it's really quite simple. All you have to do is go to the table, look for lead, and see if iron, in this case, is less reactive or more reactive. And of course, there it is. It's more reactive. And so what this means is that lead will pull electrons from iron if it can, in order to form its reduced version. Flip that around. Lead, 0, will not give electrons to iron. It's less reactive than iron, and so no reaction will occur. So we can do that for any case where we place metals in contact with each other. Okay, to sum up, if we have components coming into contact, there's possibility that we'll see a redox reaction. One of the tools we use to help predict what's going to occur is the metal reactivity series. This will help us to determine if a reaction occurs and what that reaction will be. Okay, so for your homework, please do the Competing for Electrons worksheet and go ahead and read the notes from today. Thank you and have a great night.